Hello, my name is Markus Buehler, and I serve as the section editor for the new MRS Bulletin Impact section that publishes now original research. I am very pleased today to be talking with Professor Huajian Gao, Distinguished University Professor in the School of Mechanical and Aerospace Engineering at Nanyang Technological University, or NTU, in Singapore. And he's also the Scientific Director of the Institute of High Performance Computing there. Joining us also today is his PhD student, Gao and Ni of Brown University, who has recently defended his thesis, I think last fall. Today we'll be discussing work that Professor Gao and Gao and Ni have recently published in MRS Bulletin Impact titled A Deep Learning Approach to the Inverse Problem of Modulus Identification in Elasticity. In this paper, they report the development of a deep learning method to predict the Young's modulus, measuring the rigidity of a material based on strain data that may be the result, for instance, of an experiment. The method is highly efficient and offers real-time solutions to problems that usually require complex numerical methods that rely on variational approaches to solve elasticity problems, such as finite element analyses. This type of approach may change the way we interpret experimental data and model materials. On behalf of MRS, I would like to thank you for contributing to Impact. Your article has seen 4 citations already as of today, and your paper is one of the first ones published in the new Impact section. We're very excited about the opportunity to learn more about this work today from you. Huajian and Bo, thank you for talking with us today.
Hello, everyone. Thank you, Marcus. I would like to thank you, Marcus and MRS, for taking the time and effort to talk to us and for arranging this interview.
Yeah, thank you for having us.
Well, thank you. So I have a few questions to start off the discussion. For a general audience, please describe a little bit of what your paper is about and what are the key findings are, the key takeaways from this work.
Yeah, so what I'll do today, Marcus, is I will try to answer your questions as best as I could, and I'll ask Bo to help me, and because he's the one who actually did the work. Okay, so yeah, so regarding your question, so as you know, AI, right, artificial intelligence or machine learning, has started to fundamentally change all disciplines in science and engineering. So our field, mechanics and materials, is not it's not above it's not outside this global push. So this paper, in some sense, is a preliminary demonstration of using deep learning approach to solving inverse problem in material research, which we're interested in. As you know, the traditional engineering approach is very good for forward problems. So we usually set up a set of governing equations. So we have good, very powerful numerical method to solve them, analytical numerical methods. Then we can do experiment to validate the results. But for inverse problem, that's a problem that's a traditional approach has more difficulty, or there are some opening challenges, opening questions here. So especially as you know, the inverse problem, you have problem like non-uniqueness, or you have convergence issues, and you have non-linearity, right? So inverse problem is not a well-solved problem yet. So we have for some time I have some interest in developing some new techniques or new methods trying to try to see whether we can solve inverse problem in mechanics. And so Bo and I have been talking about it, and we identified this problem that we wrote up in this paper. Essentially, it's a preliminary demonstration using deep learning, right, to solve a specific problem of how to map elastic modules of material based on measured strain field, right? So I can maybe say a few words briefly about the background. The background is probably you can think of like a medical application of elastography, where we try to diagnose cancer cells, because cancer cells like breast cancer or prostate cancer, these are like represent some kind of a hardened tissue embedded in a healthy healthy matrix, healthy tissue matrix. So in mechanics, we can relate that to some inclusion problems, right? Like hard inclusion in a soft matrix. So the problem is in elastography, so what we could do is to apply some compressive load, trying to distort the tissue. We can use ultrasound or MRI images to measure the strain field. Those are what we can get. Okay, so currently in the current practice with elastography, usually people have some rule of thumb. They look at where the strain is large, and they say, okay, here's where the modulus is small, right, or the soft. If the deformation of the strain is small, then we say, oh, here's where hardened tissue might exist. So this is how we use the kind of intuitive rules to diagnose cancerous tissues. Right. So and you can do both, right? You can use you can treat as type of inverse problem in mechanics. You can say we have this measured data of strain fields. Let's rigorously we can rigorously solve the governing equation, try to determine the best modulus field that can match the experimental data. But that problem, the conventional method of solving inverse problem is costly. It's very expensive, right? That involves some iterative processes and expensive, so it's not very good and for high throughput application or real time where the speed of diagnosis is important, so has those challenges. But the machine learning is a new technique, right? Machine learning. So machine learning, especially deep learning, that they're very good for image processing. Okay, they can relate one image to the other. So if we can think of strain field and modulus field as two images, okay, if we put in our mind, look at two images, ask our questions, how these two images relate to each other, right? Then if you have a data which can relate to images, you can train a deep learning model. And that will give you a way of relating two images. So it doesn't matter whether it's forward or backward, it's the same. It's just from one image to the other, right? So deep learning model allows us to circumvent the issue, the difficulty of solving inverse problem. Just treat inverse problem and forward problem on an equal basis. So this is really the advantage of machine learning. So that's the motivation for us to, take on this problem. By the way, so this our specific problem is solving a one or multiple inclusions in a homogeneous matrix, right? Assuming we have data strain field. That data in the practice can be obtained from ultrasound image or MRI image, but in our case, we use elasticity equation. We use finite element method, which is numerical method, solve the forward problem. So we can solve the forward problem. So we can generate data. We use our domain knowledge to generate data, as much data as we need. Right? Then we can build this machine learning model and try to solve the inverse problem. So this is kind of a prototypical inverse problem in elasticity, and which also we think this kind of approach is basically a platform which can allow us to treat generally inverse problem. We can combine the deep learning with the domain knowledge with the traditional approaches, using traditional domain knowledge generate data, help us build deep learning model, then to solve inverse problem. We think this approach is general, can be applied to serve as a generic approach to solve inverse problem in general.
Thank you.
So in terms of key finding, right? So the key finding for this problem, I would say, basically we confirm that deep learning can learn a high dimensional mapping between strain and modulus about training over a limited portion of data. And as many people, including you, are finding is how powerful this machine learning approach are, right? It's because there's no simple relation between strain and modulus, right? As I say, in traditional approach, you do iterative solving a constraint optimization problem, try to find the best modulus that can match the experimental data or measured data. So there's no direct simple relationship between the mapping. And there's a high dimensional complex mapping. It's not clear immediately whether deep learning can actually learn this mapping. So the biggest finding we have is we confirm that deep learning can indeed learn this high dimensional map between strain and modulus.
Can I ask a question about the method a little bit? You have used, you mentioned deep learning and image processing as a way of relating images or solutions and fields. In the paper, you've used fairly novel method called a conditional generative adversarial net. And I was curious if you could talk a little bit about the method, this method in particular, and the choice of the method, why you chose this approach over other deep learning approaches.
Okay, yeah. So as you mentioned that we use the conditional generative adversary net, right? CGAN is called. And I will say a few words, and I'll let probably Bo, because Bo has become quite an expert in that. So maybe he can add some comments on this. Essentially, in general, CGAN has been this technique was discovered a few years ago, right? They've been shown by many people to be very powerful tool of image processing, right? As I mentioned just in my answer to your previous question, we're thinking what we have in mind is treating this deep learning approach as really two images. Okay, we view the measured strange fields as one image, then module distributed as another image, right? We're hypothesizing this inverse probability mechanics is basically converted into image to image translation. Okay, translate one image to another. Right? So under the hypothesis, so among these various methods of image processing, CGAN is a very powerful tool, and of course we try a few other approaches, few other different methods. We see that this method can indeed achieve sufficient accuracy, right? The other methods do not achieve nearly as good accuracy as this method. The fundamental reason is actually pretty simple, because CGAN, in a CGAN method, you don't need to define a loss function explicitly. Okay, there's a discriminator, generative discriminator. So the discriminator can allow you to adaptively learn an implicit loss function during the training. Right? So this adaptivity of the CGAN method, this competition between generator and discriminator, allow you to basically to be essentially to optimize your loss function during training. Okay, so this is very powerful. Such approach is very powerful. High dimensional mapping to different image processing or really different fields. Maybe Bo can add a few comments on that.
Sure. Yeah, just as you mentioned, actually, nowadays there are a lot of exciting development in deep learning, especially on image processing process. We actually started as a play some apps which can actually give you a picture, started a picture from just a black and white sketch. Later on, we look into it. Actually, it uses the so-called conditional generative network, general adversarial network (CGAN), this kind of method. So, and also it has a very kind of already be used in a lot of different applications, many like the artistic field. But when we see it is just as Professor Gao mentioned, we see it. Oh, it's really kind of powerful tool to connect two physical fields, two images. You imagine it's kind of two very large matrix. They can kind of connect in these two. So in then combined to this inverse problem in the engineering application, like the case elastography. In our case, we see the format actually directly matches between these two. At the same time, when we look into the code structure, we find it's really kind of smart. So it has actually used not only use a neural network to generate the picture, and also it used another neural network to serve as the loss function explicitly. So it really kind of pick up the function during the training process. So it's kind of personalized or question specified loss function. And the only thing kind of missing is that what if we use this into a quite defined robust mathematical solution for this inverse problem. So that's basically what we try. We kind of put our mechanical understanding and combine it with kind of the motivation in the engineering application, which in this case is elastography, and combine this and try the approach. And actually, quite surprisingly to me, actually, it not only can do the artist work quite well, it can also kind of give us kind of this kind of very effective engineering tools, so as kind of very robust, very good solution. That's quite surprising, actually.
Well, thank you. So building on these developments, it seems like the method is quite generic. You've demonstrated it in one case, but it seems like the method of using CGANs and other deep learning methods like this could be applied in other fields. So could you maybe talk a little bit about the next steps in your work, your own work in this field, but also broader applications of similar methods in materials research?
Yeah. Talking about next step, there are certainly many directions, right? Just like, AI has become a new tool for engineering. It's going to impact all disciplines, all fields, right? I think there's multiple directions depend on the interest and the resource, right, and the time. So I think for example, I can think of for inverse problem. Just talk about inverse problem. I say in the beginning, right? We're really interested in solving using AI to solve inverse problem, because that's the weak points in existing methods, conventional methods, right? There's a non-uniqueness issues, convergence issues, and it's not very good solving nonlinear problems. So I think just for inverse problem, I can think of a few open challenges that AI may make a further impact or help us address this problem, right? So in addition to modulus mapping, I can immediately think maybe such a method can allow us to detect flaws or cracks, right? Material defects, because of the current manufacturing techniques, especially those based on additive manufacturing. So the flaws are really important, right? Really for quality control, really important issues. In addition to medical diagnosis, right? So detect flaws. A cancer cell is one of those heterogeneities, maybe, but other voids, cracks, porosities. And so that's something we can immediately extend, such a, like flaw mapping. And nonlinearity. So this paper we show is, but it's still linear, right? So we focus on linear elastic. What about nonlinear material, large deformation, right? Soft material. How do you apply similar approach to solve those issues? Those issues will often have, convergence issues or non-uniqueness become more severe. And so how do we actually solve the non-unique, how using data to help us solve the non-uniqueness problem by itself is very theoretically interesting. Mm-hmm. I think the flaw of a traditional approach is we always try to address a rigorous solution to a mathematical governing equation. If the governing equation have multiple solutions, then we sometimes have difficulty, right? Have to identify which is correct. But data, because we're talking about data. So the data itself can help us identify which is the correct solution. That's which correct solution we need. For example, you can combine with experiments, put in additional redundancy data there, right? Help you to resolve that uniqueness problem, to go beyond the traditional approach. Also for noisy data, right? Here we use finite elements, so we don't have the data noise. We just have the solution, a bunch of data points. What if you have a measurement error, right? Statistical error. How do you improve the robustness of the deep learning model? So just for the inverse problem, I think there's a bunch of challenges I can do. Maybe a couple of PhD theses, that's no problem, right? A problem, just solve inverse problem in general. And for practical, if one is interested in practical applications, I think real-time elastography, right? So because deep learning allows to do this with high speed, high efficiency. So in our paper, we demonstrated that deep learning can improve the computational speed by orders of magnitude. You can think of doing real-time elastography, completely, replace the empirical approaches. So that's immediate, medical applications, and maybe building deep learning model with combined computation experimental data. Here we use computational data to build deep learning model, but combine that with experiment. That'll be really interesting to see how to build models using experimental data or combined data. There you have noisy, right? You have experimental errors and noisy. And just for deep learning models, maybe a few things we could say there. So here, the way we combine domain knowledge and AI is we use domain knowledge, we use finite element method to generate data. That's how we how we generate data using FEM, right? So we build our domain knowledge into deep learning model. But there's other ways of incorporating domain knowledge, such as using mechanics, using governing equation to introduce a loss function to define better define so-called mechanics or physics informed loss function, right? So those you can build domain knowledge in different ways, not only generate data, but also building the knowledge into or using conservation laws to better define a loss function. And there are other methods. There's continuously emerging new tools in deep learning. One can probably introduce more deep learning models into solving these issues, in general issues in engineering. So there's multiple directions I can think of.
In terms of the method, now you've gained a lot of experience in applying deep learning to an inverse problem mechanics, which has been a long-standing problem, is a well-defined problem. What are the pitfalls, if you want to maybe share some of your insights with other researchers in the materials community broadly that are maybe interested in getting into using AI, machine learning in their research? What are the pitfalls? What are the considerations you would give them at a high level based on what you've learned in your own work?
My advice is for people, because our background is not computer science, we're engineers. I think for us, AI should be better treated. It's better to treat AI as a new tool among existing methods in our toolbox, right? We have our own elasticity, plasticity. We have our own theories and computational methods. Just think of AI as a new tool we add to this existing toolbox, right? It's not going to replace domain knowledge. So what we could bring to the table is bring our deep domain knowledge, and then we can help build better AI tool specifically for the problem that we're interested. Right? Here we show example. We use our domain knowledge to we know how to solve forward problem in mechanics, so we can generate a lot of data, right? Those data, then we can build AI model, help us solve problem that we cannot solve or we have difficulty solving, which are inverse problem. So there's examples of we can bring something unique to the table, right? We're not advancing the AI tools itself. We use as a tool, and combined with our domain knowledge, we solve the problem of engineering interest. And so I think another advice is AI, in my mind, just like an internet. I can compare AI to the internet. Like internet appears in the 1990s, right? And people were already very excited at that time, right? But we don't know what application it has. People don't know exactly. We just know internet's going to be a big thing for the economy, right? But during the last 2 decades, you see internet is permeating in all branches of commerce, into how we learn things, impact our learning, impact business, practically change our life, right? Now we're dependent on YouTube or depends on Google, and so impact every aspect of our life. I think AI is going to be similar. AI is going to be, as time goes, it will creep in all corners into everywhere in our discipline, in our fields. We just have to keep an eye and keep learning, right? We just keep learning what's available, what are the new tools, and keep an open mind and combine what we know and keep a knowledge of what our challenging problems are, what our interests are, and see if those new tools can help us.
Maybe I can just add in one point on that. Yeah. So it's actually, just as Professor mentioned, it's really kind of the front line of this kind of interdiscipline process. So actually, from my own experience during this work, actually, what I'm learning not only is kind of we need to kind of really keep learning these new tools, also how to combine these new tools with our domain knowledge. This part actually is also kind of is a kind of key part for actually from my experience. So this one, we use the SIGAN as a very good method, but at the same time, we also have to think about how to prepare the data. So we're facing the problem of elastography, but we also have to but all the possible distribution of the modulus is really kind of unlimited. So you have a very kind of practical problem ahead of us. So we use the knowledge learned from the doctors. So to abstract the typical distribution of the modulus in this question of interest. For example, here we simplify into this kind of multiple inclusion in matrix kind of distribution, and also how to kind of describe that space. All these actually use the knowledge which has already accumulated either in the application side or in the mechanical side. Then actually how to kind of manipulate this data in different format and prepare them for the machine learning or deep learning tools. So that is also kind of very exciting and also sometimes can be challenging process in this.
Thank you, Huajian and Bo, and congratulations again on a very exciting and very important work that you've published in MRS Bulletin Impact. I look forward to chatting more with you in the future, and I want to thank you again for joining us today. For more news, visit the MRS Bulletin website at mrsbulletin.org and also follow us on Twitter at MRS Bulletin. And with that, I want to thank you again for listening, and I hope to see you soon.